In this video, we'll be introducing the concept of representations of functions as power series. Now, we had our introduction to power series in the previous set of videos. A power series, in general, took on the following form. So this was the sum from n equals 0 to infinity of c sub n times x raised to the n power. This was one that was centered at x equals 0. So constant term plus an x term plus an x squared term plus an x cubed term, and so forth and so on. What we're going to be doing in this section is talking about how we can turn that power series into a particular function. Now, with this in mind, one of the big things that we did for power series in the previous section was determine an interval of convergence. As it pertains to what we're doing here, an interval of convergence for this power series is going to correspond to the domain of a given function. That is, the set of all values of x that will actually give us a specific value. Now, all of this is going to be based off of the following power series. So one possible representation would be this. The sum from n equals 0 to infinity of simply x raised to the nth power. So every single coefficient that we're going to see is going to wind up being 1. However, quite some time ago, we didn't represent that as a power series, we referred to that as a geometric series. You'll notice that the common ratio as we go from term to term is simply going to be whatever the value of x is. The sum of a geometric series is supposed to be the first term divided by 1 minus the common ratio. Common ratio in this case would be x. Now, the difference between these two forms is that this form on the right is referred to as the series form of the function, whereas this form is referred to as the closed form. Closed form is a form in which we would just plug something in and evaluate, and the series form actually expands it as a power series. Now, with this in mind, it's also possible to make small alterations to this so that we can represent other things as power series as well. The big idea is that if we can consider a numerator to be a first term and a denominator to be in the form 1 minus some other function of x, then it's possible to transpose this into something like this. This would be a geometric series with first term h of x and common ratio g of x. So this would be the sum from n equals 0 to infinity of h of x times g of x raised to the nth power. So essentially take this form that we had up here, replace all of the x's with some other function of x, and then multiply both sides by this h of x. Now, this also operates under the assumption that g of x must be in between -1 and +1 in order for the sum of a geometric series to actually work out. So to give you an idea of how this works, let's represent f of x equals 2 divided by 3 minus x as a power series. Now, the big idea for us is that this number down here, the first number in the denominator that is then going to subtract something, that must be 1. Now, there are a couple of different ways that we can turn a 3 into a 1. We could subtract 2 from it, we could divide 3. So a couple different ways that we could approach something like this. I would say the most basic would be to multiply top and bottom by 1/3. Now, that 1/3 is going to distribute through to both the numerator as well as the denominator. So numerator is going to be 2/3. Denominator is going to be 1 minus x over 3. Now, if we liken this back to the geometric series formula, this 2/3 is representing your first term, and this x over 3 is representing your common ratio. We're essentially changing it from this formula back into the geometric series that would have caused this. That would be the sum from n equals 0 to infinity of the first term times our common ratio, raised to the nth power. Now, if you're interested in leaving it in this form, there's nothing wrong with that. If you wanted to get a domain for this function, the domain is going to be the same as the interval of convergence. We would need that our common ratio is in between -1 and +1, with the possibility of equality on either end. That lets us know that this thing is going to converge between x equals +3 and x equals -3. You'll notice, though, that the original function, if we set that denominator equal to 0, would have a domain issue at x equals 3 anyway, so I guarantee you that it's not equality on that side. Now, if you're interested, you could perform a little bit of additional algebra and say that this is the sum from n equals 0 to infinity of 2 over, this denominator would be 3 to the n, multiply by another 3, and we have 3 to the n plus 1. That'll be multiplied by x to the n. That was distributing the power through to the numerator and denominator, and then combining like factors in the denominator. So writing out the first few terms of this thing, n equals 0 would provide us 2/3. N equals 1 would be 2/9 times x. N equals 2 would correspond to 2 over 27 x squared. And n equals 3 would give us 2 over 81 x cubed, and so forth and so on. Now, any partial sum that you do for this series is going to give you a pretty decent approximation of whatever your power series is. Now, let's say that I had opted to do this one in a slightly different way. Let's try this one more time. F of x is equal to 2 over 3 minus x. What I'm going to do is talk about how to shift the center. Now, quite obviously, the center cannot be equal to 3, because again, we are going to have a domain issue there. For shifting the center, I'm going to shift the center to a completely arbitrary value. Let's go x equals 8. Now, in order to shift the center for a power series, that means that in this position right here, rather than just having an x, we're going to need to see an x minus 8. Here's how we can obtain an x minus 8 in that position. So currently we have 3 minus. What we're going to do is change this into x minus 8 plus 8. This is the old mathematical technique of adding 0. Now we're going to take the x minus 8 and keep that together. And we're going to distribute this minus sign to both of those terms. So this will be 3 minus x minus 8. And distributing the minus sign to the plus 8, we'll get a minus 8 there as well. If you were to expand the denominator completely, you would still get 3 minus x. We just need this x minus 8 grouped together. What we can do is gather together the common terms 3 and -8 and turn that into -5. Now, once we have our shifted center, the next thing that we're going to need is to make sure that this guy right here is 1. So we'll do the same thing as what we did for the previous example and divide top and bottom by -5. When we do that, we're going to get -2/5 divided by 1 plus x minus 8 over 5. Now, unfortunately, we needed this plus to stay minus, so what we're going to do in response to that is call it minus a negative. I guess I probably could have done that in the first place. So now our common ratio is going to be this negative x minus 8 over 5, and our first term is going to be this -2/5. So changing this back into a geometric series or power series will be the following. This will be the sum from n equals 0 to infinity of, first term is -2/5. Common ratio is going to be negative x minus 8 over 5 raised to the nth power. Now again, if you wanted to simply leave it in this form, there's nothing wrong with doing that. But in the event that you want it to be a little bit more specific, this will actually give us an alternator in here, this negative raised to the nth power. We also have another negative out in front, so that would be negative 1 to the n plus 1. So negative 1 to the n plus 1. We would also have a 2 left over from the numerator. From the denominator, we have 5 to the n times an additional 5. That'll be 5 over n plus 1 times x minus 8 raised to the nth power. Now, if we were looking for a domain for this, domain is going to be the same as whatever the interval of convergence is. So that negative x minus 8 over 5 would have to be in between negative 1 and positive 1. Multiplying through by negative 1, we'll change this to a positive 1 and reverse the sign, change this to a negative 1 and reverse the sign, and we would be left with exactly the same thing as what we had before. Multiplying through by 5 will give us negative 5 is less than x minus 8, which is less than 5. Sorry, I forgot how to multiply 5 by 1 for a second. And then add 8 through. Now it comes as no surprise to me that one of the endpoints is once again x equals 3. The reason that that's no surprise to me is due to the fact that, once again, x equals 3 was a domain issue of the original function. Therefore, a power series representation really shouldn't cross the vertical asymptote that occurs at that domain issue.